We know how to get pH or POH if we start with an H3O plus or OH minus concentration, but now let's talk about how to get the pH if we just start with a molecule. And specifically, we're going to start about how to get the pH if we start with a certain amount of a strong acid or a strong base. The good news is these are really, really easy problems because strong acids and bases ionize completely. So that makes life really, really simple. So we see, let me get my pen out. In this first equation, HA just stands for generic acid, doesn't matter. And we know it's a strong acid because we have this forward arrow here. And we can see that my strong acid is going to donate his hydrogen to produce H3O plus and H3O plus and A minus. Since these strong acids ionize completely, however much of this I started with, all of that is going to be converted into H3O plus because it's a 1-to-1 ratio, and this forward arrow means that all of my reactants essentially react. So if I know how much acid I started with, I know how much H3O plus I'm going to produce. And if I know how much H3O plus I'm going to produce, I can just directly get that pH. Really, really, really simple. One little note, we do have one polyprotic strong acid, sulfuric acid, H2SO4. Acids only give away one hydrogen at a time. So I'll have that H2SO4 reacting with water, and it'll only donate that first hydrogen. So I'll get HSO4 minus and H3O plus. Now it is true that this HSO4 minus can then react with water, but this is now a weak acid. It's going to produce S2SO4 2 minus and some more H3O plus. And because this is a weak acid, it produces so much less H3O plus that we can basically ignore it. And we really just focus on this first equation up here. So for this polyprotic acid, really just assume only one hydrogen is given away and don't worry about this second step down here. So that's strong acids, nice and simple. Strong bases, really, really similar, except for strong bases, they can give away more than one hydroxide at a time. So if we have sodium hydroxide, that's just going to break apart into one sodium and one hydroxide piece. But let's say you had calcium hydroxide. I have two hydroxides there. So when this breaks apart, it produces one calcium piece and two hydroxides. So for every one calcium hydroxide I put in, I get two of these out. So it's the same idea as before. We're assuming complete ionization, but if you have more than one hydroxide, you have to account for that when you're thinking about what your OH minus concentration is. But after that, really simple. You have your OH minus concentration. I think the easiest thing to do is go directly to your POH and then use this relationship to get your pH. You could turn this into an H3O plus, and then from there go to pH. That's also fine. I just like this way, so that's the way I'm going to show us. All right, let's look at a couple examples. Super simple. Calculate the pH for the following solutions at 25 degrees Celsius. The only reason it's telling us 25 degrees Celsius is because those equations we learned, for instance, pH and POH add up to 14, only strictly apply at this temperature. That's the only reason it's giving us that. So 2.50 molar H2SO4. First thing we do is we have to look at this and say, okay, that is a strong acid, which means that all of that strong acid is going to be converted into 2.50 molar H3O plus. Now that I know how much H3O plus, really easy, the pH is just the negative log of that H3O plus concentration, so that 2.50, 2.5. And so we find that my pH is equal to negative 0. Now we have 3 sig figs here, so we're going to need 3 decimal places, so 0.398. You can have a negative pH. If you have a really strong acid, it can be negative. It's not that common, but this is a pretty concentrated strong acid, so we say, all right, that must be fine. So I have my pH of my strong acid. Super simple. All right, next one. 0.185 molar of NaOH. So we say, all right, NaOH, that's a strong base, and there's only one hydroxide here, so this means I'm going to turn all of this into 0.185 molar OH minus concentration. So easiest thing I think is to go ahead and get the POH initially, which is the negative log of that 0.185, because all of that sodium hydroxide turned into OH minus. So we just need to calculate that, negative log of 0.185, and we find that we get, all right, again, 3 decimal places, or 3 sig figs, so I'm going to need 3 decimal places, so 0.733. Now I can't stop here. This is the POH, and it asks for the pH, but really simple. pH is just going to be 14 minus 0.733. So 14 minus that, oops, sorry, I'm calculating, is going to be 13.267. So easy. So I get my pH right there. All right, last example, calcium hydroxide up here. I'm going to put it up here so we have space. Again, it's 0.185 molar, but now I produce those 2 hydroxides. So in that case, my OH minus concentration is going to be 2 times the 0.185, because for every one of these, I'm going to produce 2 hydroxides. So if I do 2 times 0.185, my OH minus concentration is going to be 0.370. And now I'm going to do exactly what I did before. My POH is just the negative log of my OH minus concentration. So I'm going to take the negative log of that, and I get 0.432. And then for my pH, I have to do 14 minus my POH. So I do that guy, and I get 13.568. So notice that bases, I always like to say bases are obnoxious. They always require one extra step. For the acid, we went directly to the H3O plus and then to the pH. For the bases, it requires an in-between. We go from the OH minus to the POH and then to the pH. So bases are obnoxious, and they're always going to ask us for one extra step.